Welcome to the 15th topic. We're now looking at the processor, also known as the CPU. Two terms pretty much synonymous in this context. So actually this topic is called hardware. It's a kind of a large topic, and I've decided to split it up into two videos. So in this video we're covering points in yellow, and also we're going to cover memory too, because you kind of need to understand memory before you can talk about the CPU, and we're going to cover the green points in the next video. I was actually asked to split it up, and it seems like a good idea anyway, because there is a lot to cover. We're going to be looking at a lot about specifics of the CPU, and then we're going to be looking at assembly code too. Let's begin, like I say, by looking at memory. It's not really clear how much you need to know. It just says memory, which is very helpful. So I'm going to talk about memory that I would include if I was writing my own GCSE course. So yes, so you do need to know about main memory, because that's very integral to the CPU's process. So when we say main memory, we're usually referring to RAM. In fact, if you're saying memory at all, usually you're referring to RAM. And so RAM stands for random access memory, and it's a name it has because anything stored in the RAM can be accessed in roughly the same amount of time. So that's probably something you don't need to know, but this means that it doesn't matter where actually the data is stored on the RAM, it will be accessed in about the same amount of time. Whereas if you're storing it on some secondary storage like a hard disk, we'll talk about these in the next video, but the time it takes, so the latency to get the data, varies a lot depending on where it actually is. If it's in like the outside of a disk or inside the disk, wherever it is, it can be slower. So RAM is called that, and RAM is very quick, and so the technology has quick read and write times, and so the function of RAM in our computers is to load open programs and operating system data currently in use from the slower secondary storage, so it will be sort of permanently stored on our secondary storage, our hard disk maybe, and then it will be loaded into the RAM when it's in use, because it's a lot quicker, and also it can be accessed directly by the CPU. To access data on the hard disk, it has to go through other channels, input-output channels, whereas the CPU is directly connected to the main memory, as we'll see. So this is something called a memory hierarchy. You can see we've got our mass storage at the bottom. Technically this is all memory, but when you say storage, it usually means you're talking about this persistent large capacity storage like a hard disk or an SSD. And so we have our mass storage again. We'll look at different technologies in the next video, but it has the largest capacity in our computer. Then we'll have our RAM, which is actually quite a lot smaller capacity. Mass storage might be 2 terabytes, main memory might be 8 gigabytes, and then you have your on-chip cache, which might be in the megabytes. And so cache is in fact, so this is representing cache that's on a CPU, or in a CPU. And so static RAM, or SRAM, is faster than RAM, by that I mean dynamic RAM, but more expensive, and it's often used for CPU cache, which is so a cache in a computer is a small fast memory that stores copies of frequently accessed data from memory. So okay, let me take a step back and explain a couple of stuff here. So I've described RAM as dynamic RAM, and so again, probably something you don't need to know, so the technology that RAM is uses capacitors, and capacitors are kind of like a bucket of charge. It's quite a simplistic description, but over time they discharge and the charge is lost, and so it needs to be constantly refreshed. Static RAM doesn't need to be refreshed, which is why it's called static, but that's again probably unnecessary. So a cache in general sense is just a small store of memory. So like Google Chrome will have a cache, so it will store data for websites you frequently go on, so Twitter, YouTube, Google, and it will mean whenever you go on for these websites, it will load a lot quicker. When you go on a website you've never gone on before, it will load slightly slower than it would if it was stored in the cache, because cache is very fast, but you can't have much of cache because it's expensive, and also to do with volatility. Anyway, you often talk about levels of cache, and so on a CPU. On a CPU you often have more than one cache, and so we often talk about levels of cache, and the closest will be the one with the smallest capacity, but it will be the quickest. And so latency, actually probably not something you need to remember, but this is kind of just for time wasted waiting for a response. And because physically the level 1 cache is closest to the CPU, well, it's going to be on the CPU, but it will still be closer, it will be used first. And so whenever it looks for some data, whenever it fetches some data, it will look first in the cache, and if it's not here, it will be a cache miss, and it will go on to level 2 and level 3 and so on until it finds the data. And so you have different levels. It might be just worth talking about very quickly. So finally, another type of memory that's often contrasted with RAM is ROM, and ROM stands for read-only memory. And so this memory can only be read. In fact, it can be changed, but it's very difficult. It practically can only be read. And so it's used in small amounts in computers. It's also used in very simple devices like a calculator, but in our computers it might be used in small amounts to store essential programs like firmware. So firmware is software that works directly with hardware, and hardware doesn't really need to be updated, so the firmware doesn't need to be changed. But also like the initial programs that run when you are booting up your computer. So it might be a program that first loads some data from your hard disk onto the RAM so that the operating system can work. So that might be a simple program stored on ROM, and so a ROM chip looks like this. This is a BIOS chip. Okay, let's move on to look at the CPU, which is the actual main topic. So CPU stands for Central Processing Unit, and it's the circuitry in a computer that controls the manipulation of data. So the purpose or function of the CPU is to process data. And so often it's worth saying that we often have multiple processing units contained on one chip, and that's called a multi-core processor. We're only looking at a simple model, one architecture of a CPU, so just this would just be one core effectively. And so we're looking at 3 units in our study of the CPU. So we're looking at first the arithmetic logic unit, the ALU, and this is the circuits that perform the operations on data, so the actual calculations. So arithmetic operations, Boolean operations. We've looked at operators in the previous video. I also have a register unit made up of registers, which are quick, small stores of data, different to cache, don't get confused, that temporarily hold data, addresses and instructions being manipulated by the process. So during the calculations, certain things are stored in these registers kind of temporarily. And finally, you have a control unit, which is a circuitry that really coordinates the activities of the computer. So you might have heard the likening of a CPU to like the human brain, because really it controls the computer, and this control unit is what controls the component that controls the computer. So it's very important. So you need to know about something called a bus. You can see here we've got our main memory, so this is our RAM, and it's connected via something called a bus. And a bus is a transmission channel connecting components, usually drawn as like wires. And so the data and addresses are transferred through this bus. And we have 2 types. The first one is an address bus, and so this is what sends the actual memory location to the memory. So it only goes from the CPU to the memory. It's only one way. If an address needs to be used in a calculation or something, it will go via the data bus. And so the data bus is used to transmit the actual data to and from the memory. So this will be both ways. You might need to, as we'll see, you need to fetch data for a calculation. You then may need to store some data back in memory after you're finished doing something to it, and so it will go along the data bus. And we often talk about something called the width of a bus, and this is really the capacity of how much data can be transmitted. This is an idea we're kind of familiar with because the exam board seems to be quite keen on emphasising this. You are limited by how many bits can be used to transmit some data. So if we have an 8-bit address bus, it can only take 8 bits at a time, and so it can only locate a maximum of 256 unique locations, because that's 2 to the power 8. So that wouldn't really be sufficient. You need maybe 16, 32, 64, about that size. So also it's mentioned something called a clock, and so computers have internal clocks anyway, really for synchronizing the operation of the digital circuit. And so CPUs have clocks too, or a clock. And so the clock produces repeated alternating signals like a metronome. So this is a metronome, and in music it, I think, helps people keep to the beat. And really it's that kind of clock, not yeah, so it's that kind of clock. It's often like a crystal, and a crystal will produce alternating signals very, very regularly, like ones used in watches to regulate the time, but this is regulating a digital circuit. And we use the speed of this clock measured in hertz as an indicator of the actual CPU speed. So this is just a screenshot from Amazon of just an AMD processor, and you see we've got 6 cores here, so it's got 6 processing units on one chip, and you can see our clock speed here, it's in gigahertz. And so I'm not sure which one is the actual one. I imagine maybe this is maybe overclocked speed. So you can, overclocking is where you increase the clock speed above what I guess it's shipped to you with, so you can try and speed the clock up to increase the CPU speed. And you can see we've got 8 megabytes of level 3 cache. So now hopefully you'll be able to sort of, if you're buying a processor, you'll now understand what this stuff means. Okay, let's move on to look at something called the stored program concept. So this is the idea that program instructions, just like data, can be stored in the main memory. And this may seem like a very obvious idea. It's not just data that's stored in memory, it's instructions of programs too. But actually, early computers had their programs built into the control unit of the CPU. And that meant that wiring had to be changed whenever different instructions were being executed. So if you built a computer that did one program, you couldn't then just load another program, you'd have to change the actual wiring, and that'd be a nightmare. And so fortunately, eventually, I say eventually, in 1948, Manchester Baby, it's got a long name, but this is kind of a nickname they gave it, I think, from a University of Manchester. They built this computer, which was the first stored program computer, and you didn't have to change the wiring of the CPU, and that's very fortunate for us. It seems really obvious now, but until you sort of learn about the history a little bit, I've been trying to learn about some of the history behind some of these concepts, and it helps you understand a bit better. So this is what the stored program concept. Now the CPU takes the program instructions from the main memory, decodes the instructions, and executes them, and that's called the fetch execute cycle. So it's usually called fetch execute. Kind of has 4 stages. We're going to talk about 3 of them. So that's fetching, decoding, and executing an instruction. So the first one, fetch. The fetch stage is when the CPU receives the address of the next instruction to be executed from a register called the program counter. If we just bring up, I'm going to talk about 2 specific registers. I think the program counter is the most important one. The current instruction register is relatively important too. There are other registers I'm going to miss out, kind of intermediate registers that are kind of like buffers, which I think if we were doing an A-level video I'd include them, but I don't want to swamp you with too much information. So the program counter register is what stores the memory location of the next instruction to be executed, and it increments, so updates with the next address after the end of the fetch stage. So it's constantly updating as the cycles are going through. And so the address from the program counter is added to the address bus, so sent along the address bus, and the main memory receives it and then transfers the instruction in that location via the data bus back to the CPU. And then this instruction is stored in the current instruction register. So that's the end of the fetch stage. This is actually the stage that's got the most information in. Like I say, I've missed bits of it out, but not crucial bits that won't hinder you understanding it. So the decode stage is now involving the control unit, and so the control unit will try and make sense of the instruction. It needs to decompose it into individual components. So we have an opcode and we have the operand. This will be covered in a couple of minutes when we look at assembly code, and so it makes sense of this instruction according to the instruction set, and this will make sense in a couple of minutes. And so based on this, it will sort of prepare any appropriate circuitry for the execute stage, and this will mainly revolve around the arithmetic logic unit. This is what really does the calculations. It may involve other bits of circuitry too. If it's an arithmetic calculation, it will definitely use the ALU, and so the control unit will activate and then transfer data to that unit, and then the output will be stored after it's executed, and then it will be potentially stored in a different register or back to RAM eventually. So that's the fetch execute cycle. Try and learn as much of this as you can. It's not easy. There is a lot more information, like I say, I've left out, so it is a little bit complicated, but this could be, you know, a 6, 7, 8 mark question, and you don't want to lose marks like that. So now I want to look at assembly code, and the first thing we should say, and we've kind of talked about this, and when we look at translators in a couple of topics time, this will make a bit more sense. But when computer programs are executed by a process, it's executed as machine code. So the data and instructions being transferred around in the fetch execute cycle, they're all in 1s and 0s, so they're just in binary patterns, and so they're executed as machine code by the processor. And so when you translate from a high level language like Python, Java, again this is covered in a future video, it's kind of difficult, each high level instruction is split into smaller low level instructions, and assembly code is a low level language, these low level instructions are split into something called an opcode or operator, which is for basic machine operation, so adding, subtracting, and then you have the operand, which is the data used. So 5 plus 6, 5 and 6 are the operands, and add is the operator or opcode. And so binary numbers are very difficult to understand, and so we don't want to code in machine code because it's very difficult. I mean, I've added colours and spaces here, but you wouldn't be able to make sense of what this means. So assembly language was created, and it's still very low level. It's still nothing really like our high level languages. It's still harder, it's still longer to write. It takes a lot more writing to convey the same message. So this is what assembly language might look like. So we're adding 10 to the fifth register. So assembly language uses mnemonics, very difficult word to say and write. So in this case, they're three-letter words in capitals. So this is move and this is subtract, and they're short codes representing the instructions, so the opcode. And so this here, this hashtag or hash character, it refers to an addressing type called immediate addressing, and it basically means that 10 is the actual bit of data being added to the fifth register. So it's not just a value in a register. When we write R5 or R2 or R8, that's that register number. It's the address of that register number, so whatever's contained in that register. This is the actual data. We're actually moving 10. 10 is not a register name, it's being moved to the fifth register, or added. So that's quite important. This is a literal value in that sense. So the actual mnemonics used and the actual binary codes are unique for each process, so this is really important. The patterns of zeros and ones that a particular process recognises as commands is its instruction set. So an instruction set is basically this. This is for a different processor. So we're the processor that the Edexcel exams assembly code is based on is an ARM processor. Not sure which processor this is, but it's going to be different to the ARM processor, and even different ARM processors will have different instruction sets. So basically it means that the assembly code or machine code for one processor won't work on another, so it's unique, which makes it even less easy to work out what this means. So you can see here we've got our operands here. They're different mnemonics, they're longer than we have to deal with, and you've got our opcode here, which is often written in both binary and hexadecimal for human sake. So yes. The example would have been quite helpful actually in my specification. They've included a lot of information about this, and so I'm just going to take you through it. So the first thing to say is you're not going to be expected, fortunately, to actually have to write programs in assembly language. That is quite difficult. You are going to be able to have to be able to explain what some assembly code does in the exam potentially. It's not as hard as it maybe sounds, because you're going to be given a table. So there's a long list of of the a bit like an instruction set. A bit like an instruction set of the instructions, but you are going to be, if you're doing you don't need to memorize it. No need, because it will be an appropriate extract in the exam. So like I say, it's this special ARM processor, and it has 16 general purpose registers, so R0 to R15, but these R13 to 15 have special significance. I did look up what these do. I think one of them is the program counter, and two others are slightly different, so maybe best to avoid those, but you're not going to be asked to write anything, so it doesn't matter so much. Oh yeah, current program status register, okay, and ALU flags, that'll be in the next bit. So it does say we've got the immediate value, so like 9, that would be an immediate value. This is the hashtag we looked at before. And so this is the actual table that might be replicated in the exam. So you can see all these different operations. There's more on the next slide, and you can see kind of like these are kind of like variables. So this would be replaced by, you know, the number, so 5 up to 15. So it would be like R5. That stands for register 5. And you have service condition. I'll show you an example in a minute. And the other ones, the rest of the table, you have these branching operations, and this just means kind of little basically move lines. So move lines based on a condition, and so compare is just sort of evaluating to true or false. If the value is in the register, it will be true. If it's not, it will be false. And so you have these conditions. So in all of these are conditions, and these are even smaller mnemonics for are like our operators. So equal, not equal, like that. And so these are just added after. So if we wanted to branch if we want to branch if it's not equal to, we write B BNE. So if you see BNE, that means branch not equal to. And this is branching not equal to. It's referring to these status flags. And so as it says here, the compare instruction always updates the status of the flags. So these are flags that are in the program status register, and these will update based on what's happening kind of above it, if you think of it like that. And so it really, it's not worth overthinking this too much, because it actually, let me move on and show you an example here. What else we need to talk about? Not much. Okay, so just one example. I'm afraid they're not easy to come up with, because I've got experience working with slightly different assembly languages, not this actual one. So this is my sort of pseudocode. Then I try to write some assembly language for this pseudocode. So here we've got, but basically this code is saying if variable b equals variable a, then we're going to set c to 6, and then we're going to just anyway set d to e. So relatively simple. I think the code you'll be shown will pretty much only be if statements, because it's difficult, I think, or there's not a way to do while with what they've given you. So what this code is doing, let's annotate it a bit. So the first thing we talk about is the first line, so compare, and so we're comparing R1 to R2. This is the one we're kind of focusing on in the first position, and this is our, both operands, but this is what we're comparing to. So if R1 is equal to R2, this is, as we say, branch not equal to. End if here and end if here, they're both examples of something called a label. And so a label is really kind of like a pointer to a line. So basically what we're saying is if the value, if this is not true, if the value in R1 is not the same as R2, then we're going to branch to here. So we're going to skip this stage and go here. If this is true, if the value in R1 is the same as the value in R2, this line will be executed, and this line will be executed anyway, because it's after the label, and this will be executed. So hopefully you can see what's happening there. As you can see, R1 is kind of being matched by A, and then B is R2, and so on. So the registers are kind of taking place of the variables. So this is the kind of thing you're going to have to do. So it will probably be set in context, and so you need to try and work out what it's doing. I can't be too much more helpful in this, because it's very much to do with what they give you in the exam. But basically, you've got to use the table to try and work out what's happening here. So you've got to, yeah, basically just compare like what's written in their example to the table, and they'll give you enough information in the table. But the main bit is really branching, and it's just where the idea that you can skip lines based on these conditions. Okay, hopefully that was useful. Yeah, thank you for watching.